get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. I'm sorry we're starting a little bit late here, so let's not waste any more time. Let's jump right in. See here. This is us. Okay, so last time we were talking about limits, obviously, and we pretty much finished everything that we wanted to do for now in terms of, knowing how to compute them, knowing what they mean, knowing what they are, all that good stuff. We're going to be doing more with limits, but nothing by way of learning how to compute them now for a while. So, yeah. There are some important takeaways. I just want to make sure that you remember all these things with limits. So I guess we'll start there. So remember, a limit, know what a limit is and what it cares about. So a limit doesn't care about being at a certain point. It cares about getting close to a certain point. So never mix that up. Limits are like the y values that you're approaching when your x value is approaching something. So limits are you basically tracking the y values. And it's all about proximity, about getting close. It doesn't matter whether you get to the point or not. That should be clear. Your function might not be defined at the point. The limit doesn't care. Limit will exist if both the one-sided limits exist and agree. And there are some times when you must check the one-sided limits. Some common situations where this will come up is with things like piecewise functions or absolute values. If you're at the point where the thing inside the absolute value switches from negative to positive, you normally have to take both sides from there to make sure everything is okay. And just like in general, whenever you're in a weird situation and you're not really sure how to proceed, you might want to be careful and just, approach carefully one side at a time. That being said, I will also say you should know the limit strategies and the properties that I gave you, very important. And you will need to know all those for the quiz. You guys have a quiz coming up. You have a quiz this week. So yeah, don't forget that stuff. So with that being said, we're actually going to move on to the next topic, which, as you see there in the title, is continuity. So let's actually jump into it. So continuity is a very important topic. I like how skinny that is. So we're going to talk about continuity. So this is going to involve limits, but it's not really, we're not going to learn anything new about the limits part. So let's actually talk about that. So let's jump into the definition. We say f of x is continuous at the point where x equals a if the following equation holds. Limit as x approaches a of f of x is equal to f of a. So this is what we call continuous at a point. So I want to emphasize here that I'm talking about continuity at a point. Okay. So if I'm at a coordinate where my x value is a, if this equation holds, this means I am continuous at x equals a. Okay. Now here's another definition. We say f is continuous, like continuous in general, just not continuous at a point, it's continuous. If it is continuous at every point in its domain, i.e. the above equation holds for all a in the domain of the function. So once your x value is in your domain, that equation is going to be true. And if that is the case, we call such a function a continuous function. So this is our definition of continuity. Now, the above are the definitions. I expect you to use in quizzes, tests. Below, we give, put an exclamation point here, an intuitive definition, right? Because sometimes I'm also going to ask you questions when I'm giving you a picture. So you might not want to actually check an equation. You might want to know, what does continuity really mean? So what do I know to look for? And so that's what I also want to give you now. But that being said, this is the intuitive definition, and it's not like with limits where I was like, okay, the intuitive definition is all we need to know. In this case, I expect you to know the real definition, but the intuitive definition can help you out a little bit. So there are going to be times when I'm going to ask you to show that a function is continuous or tell me why something is continuous. And I don't expect you to tell me the intuitive definition. I expect you to show me that this equation is true, okay? But what does it actually mean to be continuous, right? So kind of means what you probably think it means. So intuitively, we say f is continuous at x equals a if in some region around a, the graph of f has no breaks, gaps, holes, disruptions, etc. It just kind of continually flows. So in theory, you could graph f without lifting your pencil off the page. Right? But that's just in theory, because the function might actually be super difficult for you to graph, and you might not know how to graph it, and you wouldn't want to do that anyway. But this is just kind of intuitively what I mean when I say continuous. It continually goes, right? So you don't have to, there's no disruption, no breaks. It's just flowing consistently. But at the same time, if I ask you on a test, why is this function continuous? And you tell me, well, I can sketch it without lifting my pencil off the page. I'm like, no, it doesn't work. You know? So I'm like, well, it's continuous because I can do this. Oh yeah, do it right now. Let me see, sketch it right now. Like you don't know, you might not be able to sketch the function. But that's kind of the idea we're going for. Now, it might seem strange that if this is the intuition we're going for, that this equation actually accomplishes that. I mean, it's just one little equation with a limit inside of it. How do I know that when this equation is true, that this kind of intuition will actually work out? Let me actually show you some examples. And I'm not proving anything because I'm only going to show you a few examples when there's an infinite variety of possibilities. But just to kind of compel you towards believing me. So here's an example of a continuous function. Okay, so here's my function. Well, these are the axes. And my function is just +. And this is the point A right here. And you'll notice that I can literally just graph through A without lifting my pencil off the page, right? Something crazy might happen further out, like far away, but when I'm in the local neighborhood of where A is, I literally can just a continual curve, very nice, no disruptions, no breaks, no gaps, no holes, no nothing. It's just flowing as I pass through A, right? Nothing wrong. It's almost unremarkable. So let me actually show you some of the things like what not continuous would look like. AKA what we often call this is discontinuous. Okay, so here are some examples of discontinuous functions. So here's one example. Hole. Okay. So here is A. Right? Now that's not continuous because it has a hole, which means if I'm drawing, I'd have to jump over the hole to get to the other side and continue drawing, right? I couldn't just right? Because there's a hole there. I'm not allowed to touch that part, right? So there's obviously a disruption. It's not continuous at A, right? So here's another one. So something like so again, notice that at A, I can't just keep drawing. I have to like jump up. There's a whole gap there, right? Not continuous. Again, sort of very intuitive. Like if I showed you these pictures and asked you to guess which one was continuous, you would have guessed the top one, right? So very intuitive, but in math, we can't rely only on our intuition. So we need to know how the equations are going to guide us here. Here's some other examples. So similar to the first one, but this time I'm going to fill in the hole up here. So again, not continuous at A. Obviously, I have to lift my pencil up to fill in the hole, then come back and start drawing again. Another one. So I have a function doing this. And I have another one here, and here. So none of these functions here are continuous. You'll notice that they all have some sort of disruption going on as I'm passing through A. I have to jump over a hole or jump up to a gap or fill in a hole and come back, or one side goes off on an asymptote and the other side is just chilling. Like there's something crazy going on that breaks up the function, right? And I will submit to you that whenever something like this happens, no matter what variety or form it happens in, it happens because this equation is not true. And whenever something nice happens in this sense, like this first one, it turns out that the equation I told you was true. Let me show you. So suppose I call this B, right? Let's call this B, call that C. Call this B, call that C, call this B. Okay, let's actually look at it, right? If I were to go through and try to actually do these, find these things that are in the equation, what can I say? Well, f of A is, well, it's undefined. It's not even a thing here. The limit, does the limit exist? Sure, I can take the limit. I will actually get the answer B, but obviously it's clear that the number, whatever number B represents is a number. It's not undefined. So obviously the limit does not equal the value of the function at the point, right? F of A isn't even a thing. It's not defined. The right side of this equation doesn't work. Okay, what about over here? You're going to notice that in this case, F of A is defined. In fact, it's B. What is the limit in this case? Not rhetorical. I'm actually waiting on someone to.
It doesn't exist.
Doesn't exist. How do you know?
Because if you look at it like as a one-sided limit,
Mm-hmm.
they don't equal each other.
Right, because the limit as x approaches A from the right side of f of x is going to be C, and that's not the same as the limit as x approaches A from the left side of f of x, which is B. And so again, you end up with the limit as x approaches A of f of x does not equal f of B, f of A. Right? So once again, so in the first case, the limit was fine, but the function itself kind of messed up, doesn't have a definition. Here, the function is fine. It's defined at the point, but the limit messed up. So you're saying, okay, well, maybe both the limit and these guys can work, but it's and everything will be fine. But you have to be very careful. Look at this this example right here. Clearly, that's not continuous by our definition. And you will notice that both the function and the limit are defined here, but they're not defined to be the same thing. Right here, if I were to look at f of A, the answer is C. And if I were to find the limit as x approaches A, the answer is B. And clearly, B and C aren't the same. You can see the positive distance between them here. So once again, not equal. We're in a situation where both the function and the limit, you can compute them. They make sense. They're defined, but they're not the same. And what happens is you get a behavior like this. There's a hole that you have to fill in somewhere else, right? Whenever the function isn't defined at a single point, but the limit is okay, it means you just have a hole. If the limit doesn't exist, but the function is fine, you have like a jump. There's a gap, right? Similarly here, the same kind of thing is going to happen. The function is going to be defined, but the limit as x approaches Okay, can you guys hear me? Say something, Mika, so I'm sure I
Go
can
ahead.
hear you.
Yes.
Okay, awesome. Okay, so here, if we look at it, as we're coming from the left, it's infinity. If we look at the limit coming from the right, it's b. So obviously, the limit as x approaches a of f of x does not exist. And obviously, that means it's not equal to f of a. Right? And so I'm showing you with these few examples. So it can't be a general proof because you can't prove a general statement by just using a finite number of examples. But hopefully this is starting to convince you why this equation is actually important. You'll realize no matter what, come up with any situation you want. It doesn't matter. If it's not continuous, this equation breaks. And if it is continuous, that equation is going to work. You're going to notice here that I would have f of a equals b. I would also have the limit as x approaches a of f of x equals b, and that means they're the same. And look at the result. I can graph through a without lifting my pencil off the page, right? So whenever we're continuous, this equation works, and whenever we're not continuous, it doesn't, right? It's an if and only if, right? So I can define this very intuitive idea with that equation. That's the important thing. And we call this property continuity, the property of no disruptions, no gaps, no breaks, no holes. How do I know that such a thing is occurring, even if I don't know how to graph my function or it's some sort of crazy function? Well, just check this equation, right? Because if the equation works out, it's continuous there. If it doesn't, then it's not. So, yeah. So, as the above illustrate, when we're not continuous, the equation breaks. It works when we are continuous. So now let's talk about showing continuity, because that is something you're going to have to be able to do on the quiz. Okay, so I can give you a random function and I can ask you, is this guy continuous? Or tell me where this guy is continuous, right? So it turns out there are three things. To show f of x is continuous at x equals a, we must show three things. And we've kind of been going through them. So the first thing is to show that f of a is defined, meaning I can plug in the number into my function, it should work. The moment my f of a is not defined, it's already a problem. It means that there's a hole there, right? So it's not going to work if the function isn't defined. So that's the first thing you need to check. Second thing you need to check is that the limit as we approach a of f of x exists. And of course, you should notice, may have to check the one-sided limits. So that's the second thing. And third, the values in 1 and 2 are equal, right? So the function has to work, limit has to exist, and they have to give you the same answer. Unless all of these happen, it's not continuous, right? So all of these must happen for it to be continuous. And if any one of these do not happen, then f is not continuous. At x equals a. Yeah. So by the way, what that means is, let me just be clear about this. To show continuity, you need to show all of these. To show discontinuity, just show that one of them aren't true. Right? So if you want to say that it's not continuous, you don't have to go through all three things. Like if the moment you find out that it's not defined, you just stop. Like it's done. You don't have to check the other two things even, right? But if it is, if you want to say that it is continuous, you have to actually go through all three. Okay. Let's actually do some examples. Actually, maybe I should tell you something else first. So there are things called, guys, I want to introduce, called the elementary continuous functions. The following functions are continuous, i.e. continuous on their domains. So these are what we call the elementary continuous functions that I'm going to show you guys now. So these are just very basic fundamental classes of functions that have the property that I mentioned above, and they have it everywhere on their domain. And for the most part, you're always going to just be able to assume that these things are continuous whenever you see them. So one is the class of functions called the polynomials. Right? In fact, these guys are continuous on the entire real line. We say AKA continuous everywhere. Okay? So polynomials, that's one of them. Another kind of function, rational functions. We spoke about them last time. Ratio of polynomials. These guys are also continuous on their domain, meaning as long as you're not plugging in anything that makes the denominator 0, you're golden, right? At any other point, you'll be able to sketch through it without graphing your lifting your pencil off the page. Three, radical functions. So square root of x, cube root of x, things of that sort. If this guy is continuous for 0 to infinity, you say continuous on. If n is even, right? So if you have an even radical, you have to, what's underneath the radical has to be greater than or equal to 0. We know that. And for radical n, the nth root is continuous everywhere if n is odd. Okay, so those are the radical functions. For exponential functions, we looked at those at the beginning of class. Very important functions. Most important function in calculus belongs to this class of functions. Continuous on their domain, again, you know what those guys look like the e to the x function. 5, logarithmic log functions. Now, it's kind of strange here that, remember, we know that log functions are actually inverses of exponentials. So it's almost like we're saying the same kind of function, but it's actually worth that we consider them as separate functions altogether. There are lots of things that we can learn from exponentials and logarithms than just studying logs as their own class of functions. The 6th kind of function is not one that we're going to deal with, but you should just know anyway. Trig functions. And it includes, of course, inverse trig. We won't deal with these in this class. Okay. So we don't have to worry about trig functions, but otherwise you should kind of know it. These guys are what we call the elementary continuous functions. These guys are the basic fundamental functions. They're kind of like, when it comes to functions, they're kind of like the elements in your periodic table. That's why they're called like that. They're elementals, like the 6 infinity stones of math functions, right? Like all the functions you've ever seen is like a combination of these guys, right? Everything we've seen is built up of these guys, and everything most people have seen is built up in these guys. You'll probably never see a function that's not one of these guys unless you're a math major, and things get crazy after that. But these guys are the building blocks. Everything that you've been doing in math up until now involve these functions in some way, shape, or form. And these guys are the elementary continuous functions. It's very nice to work with them because of their continuity properties. Yeah. So let's, at this point, do some examples. Okay, so the first couple we are going to do very painstakingly, even though the answer is obvious. This one is a polynomial. but I'm going to kind of show you how someone would go through and verify all the things I was telling you. And then when we get to examples like C, D, and E, it's really going to start to look closer to what I would actually test you on. But to just go through the motions here a little bit abstractly. So here we have a polynomial. I want to know where it's continuous, right? So on what interval are the following continuous? So what do? Well, here, let A be any real number. Okay. Then what we want to do is want to check, is f of A defined? Sure, it's defined. F of A is equal to A squared. So yes. Okay. Then we go and we ask ourselves the question, does the limit exist? And we can actually look at the picture here. And yeah, it's clear. For any random A I pick, and I come in from the right or come in from the left, they always bring me to the same answer. In fact, they bring me to A squared. And so what I can say is the limit as x approaches A of the function is A squared. So yes. Third, I ask, are 1 and 2 equal? And so I can say yes, right? Because they're clearly both A squared, right? The limit as x approaches A of x squared is equal to the value of the function at A, which is A squared. So this means for any A, f of x is continuous. Right? So that's how you can kind of prove for any polynomial that it's going to be continuous. And we can say here, E, f is continuous on, because the question asks for the interval, so we have to give them the interval. Boom. Right? You could also say f is continuous everywhere. So these are all equivalent statements. It's continuous for all real numbers. It's continuous on this interval. It's continuous on that. These are equivalent statements. But we were asked for so yeah, let's look at another one. So that one's a little abstract because I'm like, let A be any real number. And this one is going to be a little abstract too, but the others are going to be a little nicer. So for this one, I can do the same thing. Let A be a real number. That's my question. One thing we can say clearly, A cannot be 2 since we divide by 0. So suppose our A is in this interval. It's everything other than 2. Right? Then I can ask the question, is F defined? And I can say yes, because f of A is going to give me a squared minus 4 over a minus 2, which is a plus 2, a minus 2, which is a plus 2. And that's going to be the value it's going to give me when a is not equal to 2. It's just going to give me that value. It's just a fraction that I can reduce and get that. That's 2. Does the limit exist? And we can check the limit as x approaches a of f of x. That's just the limit as x approaches a of x squared minus 4 over x minus 2. This is just the limit as x approaches a of, well, that should be a 2. And at that point, you'll know that that's actually a plus 2. So then you ask, are 1 and 2 equal? The answer is yes. So this means our f is continuous on where? Well, everything other than 2, because that's what I assumed a was. Okay. That's that. So those are probably a little bit more abstract. So let's actually get to something more concrete. Where you can, what's going to be closer to your test. And there's some homework problems that would be useful for your test also. So let me mention that now. So the above were abstract. You will be doing problems similar to below. From now on, we will assume the elementary functions are continuous without justification. Okay. So you're allowed to do that now. From now on, you're allowed to do this from now on.
So for the quiz, we can like assume this.
Yes.
Okay.
So I'm going to show you what it would look like when you're doing something, right? So here's the problem. Tell me where this guy is continuous. And now I am going to kind of show you. Okay, so we see this problem shows up on the quiz. Jhevon says, where is this guy continuous? What are the things you should start noticing? So here's a question. It's a piecewise function, obviously. So it's not just one of the elementary functions. It's has pieces to it. So what you're going to do is you're going to first what I would notice is notice the values that your piecewise function is broken up around. These can be potential. These are potential issues. Because remember, piecewise functions are allowed to be very different from one side to the other. So if you define it in such a way that the left and right side don't connect, that's a problem, right? So you're going to want to know what x values that works for. Okay. The second thing you're going to want to notice is look at each function in here. Yeah. And see if there are other potential problem x values. Okay. So now I go and I look at my functions. And so this is what I mean you can now take for granted. So you look at this guy and you notice that this here is a rational function. So I know it's continuous. So I'm not worried about it. As long as my x is not 2, we're fine. And you'll notice that that part of the function is defined for x not equal to. So there's nothing to worry about in the top line, right? There might have been something else to worry about. So for example, if it were an x minus 5 in the denominator, then now x equals 5 is another problem spot that I have to worry about. If I look at this function, this is a polynomial. Again, it's continuous everywhere. Right? This guy's continuous for x not equal to 2 and x is not equal to 2, right? So what you want to do first is identify all the problem spots. So that was step 1. Identify all the potential issues. Okay. And that comes down to, especially in a piecewise function, you have to see what are the x values where it's stitched together, and then you're going to look individually at each functions. Is everyone okay in here, or is anything else wrong besides these x values on the outside here? So you look on the outside and you look on the inside of the functions, and you kind of examine them. And if you notice it's one of the elementary functions, the polynomial or whatever, you can just know where it's going to work, where it's not going to work, and you don't have to identify it. So here, you'll notice the following. Note, if x is not equal to 2, we are fine. The individual functions are continuous. Okay, so we need to examine x equals 2, right? So now we're going from the situation where above I had to be very abstract and be like, let a be any real number. But here, because I'm assuming all the elementary continuous functions work, I can ignore most real numbers and I only focus on the problem ones, right? Because I'm assuming everything else is going to work out, right? So really the only issue here is that x equals 2. I don't know if they actually connect on around x equals 2 based on how the functions stitch together. So that's what you're going to focus on at x equals 2. So now you want to know what's going on there. So 1, you can say, is f defined? Is it? Is f defined for 2? What is it defined as? If anything. So I'm asking what is f of 2?
Zero.
It's 0, right? So you have to remember how to read piecewise functions. It says right here, when x equals 2, the output is 0, right? Okay. So this is 0. So yes, it's defined. So now we move on to the next stage. Does the limit as I approach 2 exist? So now I go and I look at the limit as x approaches 2 of the function. Now, how do I find that limit? This is the limit of what? What is the limit as I approach 2? You guys are seeing the function. What is the answer, or what are we taking the limit of? What do you guys think?
Would it be x squared minus 4 over x minus 2?
Yeah, but it says 0 here though.
Oh, okay. Well, you were saying approaches, so I didn't know if you meant like up until 2 or like what it does equal to. So that's where I was confused.
Yeah, but what about here though? You're not worried about that? I mean, we're going close to 2, right? I mean, isn't it important to know what x equals 2 is doing?
Yeah, it equals 0.
Yeah, but so why did you ignore that though? Like you told me the top one. Why did you ignore it?
No, I was just confused for a second. I don't know.
Okay, so you're confused. Okay, so yeah, so this is what I want to make sure doesn't happen. Right? So I want to make sure, like when you gave me the answer, it was the right answer. But I need you to know that it's the right answer, know why it's the right answer. Because that's when you end up in a situation where you're on the test, you write down the right answer, and then you erase it because you have doubts in yourself. Like you need to know this is the right answer. Why is it that we do not? I didn't want to erase that. Why is it that we do not worry about this? Well, we are taking a limit. And remember, we reminded ourselves at the very beginning of class, what do limits think about being at the point? They don't care.
At the point, it's getting
Right.
close.
Limits do not care about being at the point, right? So I need you to know that you are supposed to ignore x equals 2, right? And why are you ignoring x equals 2 is because you're taking a limit. The limit doesn't care what's going on at 2, right? The limit cares what's going on close to 2, what's on the right side of 2, what's on the left side of 2, right? Which is this guy, right? That's why you're going to focus on the top part, right? So when I'm taking the limit, this is the limit I'm concerned with. Note, ignore the x equals 2 part of the function. The limit, don't care. Honey badger. It's not a mathematical term. Okay, so now we're here. Now we have to find this limit. So now we have to remember, how do I find the limit again? Oh, you go through those limit strategies. So you try to plug in, you go through that whole thing again, right? So you're going to have to know how to deal with limits in order to do this thing. So we know that strategy 2 works here. So at this point, go through the limit strategy. Strategy 2 works. Right? Don't forget your training grasshoppers. It's one of the biggest problems in math, right? Like students learn something and they're like, yeah, we get it. But then when they move on to another topic, they forget the last topic, which no bueno, it doesn't work, right? Math builds on itself. So every strategy I told you before, you still have to remember because you're going to encounter things where you need to know, well, how do I deal with this now, right? And I would have told you before, right? So here, you realize you get 4. So now you go and ask the question, are 1 and 2 equal? Well, are they? No, right? Here I got a 0. Here I got a 4. So turns out the answer is no. The limit as x approaches 2 of f of x is 4, but that's not the same as f evaluated at 2, which is 0. Okay, so now is the moment of truth. What does that mean? What can I conclude based on the work I just did?
Not continuous.
Not specific enough.
It is not continuous.
Huh?
Approaches.
What?
It's not continuous because of the at x equals 2 or at something.
At x equals 2. That is the important part. F is not continuous at x equals 2, right? That's what we just proved, right? Remember, we were focusing on 2, right? So we're not proving anything in general here. However, we did say earlier that if we're not at 2, everything's fine, right? So as long as we're not at 2, we're good. So we learned earlier that if x is not 2, we're fine. We're continuous, right? So the calculations I just showed was only for 2, right? You'll notice that I didn't put any a. I was plugging in the value 2 specifically at every point, right? So I can only make a conclusion about x equals 2, not in general. However, because previously I already mentioned that everywhere else is fine, and now we know that it doesn't work at 2, I can say f is continuous on this interval, all real numbers except 2. In particular, I didn't ask this here, but you should know in particular, f is not a continuous function. Now remember, what does it mean to be a continuous function? It means you're continuous for all points in your domain, right? Now clearly, 2 is actually in the domain of this function. I know that because of this. 2 is in the domain. I can plug in 2 and get an answer, right? However, it's not continuous at 2. Therefore, the function is not continuous at all points in its domain, and therefore, in general, it's not a continuous function. If I want to say specifically, where is it continuous, then it's continuous on this interval, but it's not continuous at 2. So yeah, so you might be curious. That's curious, right? Why did this happen? Come on. Why did this happen? Well, we actually know how to sketch this guy. We actually did it a few classes ago, quite a while ago. We know what this guy looks like, right? He actually looks like a straight line, except when passing through x equals 2, right? Hits here at 2, and here, that's 2, right? So here, this is f of x for x not equal to 2. What is f of x when it equals 2? It was 0, right? Which means that there's a point filled in here. Now, clearly, by me drawing that picture, you'll know that's not continuous. I literally had to lift my pencil up to come down to the x-axis, fill in that point, then come back up and start drawing again, right? So that's what happened, right? The thing wasn't continuous, right? We know that x squared minus 4 of x minus 2 is not continuous at 2. So someone says, you know what, I'm gonna fix this. They go and they fill in this point right here, and they messed up. Dude, you only had one job. They messed it up, right? They didn't fill in the right hole. They should have they should have filled in over here, but instead they filled in over there, right? They didn't fix the problem. So it's not continuous, right? It's still, the limit exists and the limit gives me 4, but the value of the function is 0. They don't connect, right? There's a disconnection, there's a disruption, there's a hole, right? I can't actually, it's not continuous, right? That's what happened, right? Now we can know that that would have happened from our calculations without actually knowing how to graph it, but we knew how to graph it, and it's not hard to graph this function, so might as well graph it. But you can see here, my function was defined, so I know it's filled in at the point, but my limit gave me something else. The fact that the limit exists means it's not a jump or a gap, it's literally just a hole, but that hole is not filled in the right point. So I can know how the graph is behaving at this piece without actually even knowing how to sketch it. I'll know, oh, the graph has a hole here, it's not continuous, right? And I can know it by going through that. Let's do one more, and I'll leave you guys with the others to try. Or we'll put one more to try. So this one is actually very similar. It starts out looking like the same function. So you might think, is it going to have the same answer? Actually does not have the same answer. So if I look at this one now, we'd go through the same thing, right? So I know my potential issues is that x equals 2. And I can state if x not equal to, we're fine. Right? Now I don't have to justify it, but I do have to show that I thought about it, right? So I'm just going to write it down. We're fine. How do I know we're fine? They're elementary continuous functions. I don't need to justify myself. I don't need to explain myself to you, right? When it comes to the elementary continuous functions, you don't, right? So you're like, if we're not at 2, we're fine, right? Because this guy's a polynomial, that guy's a rational function, and they both behave when x is not 2, right? So the only thing is when x is 2. So I go in and I'm like, okay, at x equals 2, 1, I see that f of 2 is, look at my function, oh, it's 4. 2, look at the limit as x approaches 2 of the function. Go up here, what should I be taking the limit of? Well, the limit doesn't care about x equals 2, so it must be the other piece. So I'm going to take the other piece. So that's 4. And that's 4, which means in 3, I can say, well, the limit as I approach 2 is actually equal to the function evaluated at 2. They both gave me 4. I can conclude from this that f is continuous at 2, right? I just did the calculations to show at 2. And then I can say, since we're fine for not being at 2, I can then make the conclusion that f is continuous everywhere. So this guy is actually a continuous function, right? We're fine when x is not 2, and we're fine when x is 2. That means we're fine everywhere, right? And like what happened now? You'll notice we were in the same situation. We had this guy doing here, going off like that, going through 2. This is f of x when x was not 2. And then someone came in and they're like, okay, you know, when x equals 2, I am going to fill in the value 4. They came and they filled in this thing. So now I can just go right over the hole. The hole isn't there anymore. We filled in the hole. So I can just draw right through without lifting my pencil off the page. It is now continuous. It's a continuous function. It's continuous at all points in its domain because all real numbers is in the domain of this function, and it's continuous for all real numbers. Okay. So let's see. So there was one more. But I would like you guys to go through the motions there, as well as you guys should probably start doing the homework because there are some slightly more exotic things that will be asked on the quiz. So for example, I might, instead of, so on the quiz, I would ask you guys things like, I'll try this for next time. So things like in quiz and homework, FYI, say quiz, homework, test. We could have questions like, so we can get a little bit more abstract. Like I can ask a question something like this. So instead of putting the 6 here, I could say put a letter K. And then I can ask, what does K need to be so that this is continuous everywhere, for example? Right? So when it comes to continuity, you should know how to recognize it from a graph. You should know how to, if I gave you a very specific function, you should know how to examine it to tell me exactly where it's continuous, where it's not, as well as if I just leave a part of a function vague and ask you, how do you need to fix this in order to make the function continuous? So for example, I could have asked like a part A of a question here, where is this function continuous? And you tell me, oh, it's continuous except at 2. And I can tell you, can you redefine the function so that it is continuous at 2? And your answer would be to redefine it this way. You'll say, oh, yes, I will change the 0 that we had to a 4 instead, and that will fix everything. So things like that you would need to know, right? So that's just a little bit more conceptual. That's kind of what you'll need to know. Well, that I will leave it there.
Wait,
Yes, question?
Yeah, where is this in the book? Because I saw in like the homework, I didn't see anything with continuity up to 2.3, which is what the quiz was on.
No, this is definitely chapter 2. I think it's 2.1.
Oh, okay.
There's something called continuity. That being said, there is I think the quiz was it said going up to derivatives. So it's like the very basic, but since the very beginning of derivatives, which we're going to do in the next class, and since we missed class on Monday, so now we're kind of slightly behind. Whatever Monday we missed it. It's been a long week. I don't remember. So we missed class one day because of some holiday or whatever was going on. And then, yeah, so we're now like a class behind. So there are a couple questions on the quiz that you guys won't be able to do. So what I will do for you guys is I will count those questions as bonus questions. So, yeah. So you might see some questions about derivatives on the quiz, but you can ignore them if you want, or you can try to study ahead and attempt them. So I'll be doing derivatives with the other class on Friday. So if you have time, you can check out that lecture and try to see how the quiz will go. And if not, it's fine, because I won't let it count towards the total. That being said, we're going to wrap up now, unless there are any other questions. I feel like Sarah was supposed to email me about something.
Yeah, I was going to email you after class.
Okay. All right. Okay. With that being said, I will let you guys go. So have a good day. Thank you for your attention. And I'll see you guys in the next one.